So this is charcoal, which does absorb inhaled agents, CO2, for example, and water, but does not absorb oxygen, nitrogen, nitrous oxide, and CO2. The use of capturing devices may become required for the continued use of desflurane. So we tested how well such a device, contraflurane, with one particular workstation, the ACES, was actually able to capture desflurane. The first revision of this paper is under review in anesthesiology. So we could get it back every day. So this is what we're talking about. This is the contraflurane, which basically is a canister holding the charcoal right here. So here is your ventilator bellows. The excess fresh gas with the vapor comes out here. It gets connected here to the charcoal filter. This is our experimental setup. We deliver desflurane here. We are ventilating a balloon into the top of which CO2 flows. And we ventilate that, and then we look at how much actually disappears from the vaporizer and how much is being captured, and we do that by weighing those two canisters. So we've been testing desflurane in oxygen air, and the CO2 inflow was 160 milliliters per minute. There were 3 parts. First of all, because before we're going to test the efficiency of the charcoal, we have to make sure that all the vapor that comes out of the vaporizer actually reaches the capturing device. So what we did was 15 runs of different phase gas flow vaporized and downsetting combinations with 160 milliliters of CO2 going into the tip of the balloon. So in order to collect, so what we did was we disconnected the exhaust here and we fed it into a Douglas bag, which collected the gases over 15 minutes. Then after 15 minutes, we wanted to know how much was in the bag and how much had disappeared. This one was easy. We just measure it on a high precision weighing scale. Here, we need first need to know what the volume of the bag is. That was easy. We added a known amount of CO2 to the bag and then measured the concentration. From that, we derived the volume of the bag. We measured the desflurane concentration, and that allowed us to determine the amount of desflurane in the Douglas bag. And so we compared those two, so the amount that disappeared here and entered here, and they were exactly the same. So no loss in between the vaporizer and the point of collection. Okay, next thing we had to determine, because we're administering both desflurane and CO2, we had to make sure what the effect of CO2 was on the charcoal whale. So what's the relation? I mean, I mentioned that the charcoal only captures inhaled agents and water. So what's the water? How does the water come into play when we're giving CO2? Because we're using granules here, and the CO2 interacts with the carbon hydroxide, generating water and heat. Here's the water. And of course, if the charcoal weight gain is used to assess the effectiveness of the charcoal to absorb inhaled agent, we need to make sure that the weight gain is not caused by other molecules like water. So how did we study the water effect? We just did the same run without desflurane. And the question was, would there be any weight change due to CO2 via its effect on generating water? And kind of surprisingly, I mean, here is the first gas flow that we used. This is the weight. This is weight gain, weight loss. We actually found an unexpected weight loss. Why that is, I don't know. Anyhow, then we proceeded to actually measure the performance, defined as capturing the device weight gain, charcoal weight gain over weight loss, doing the same set of experiments with desflurane and CO2, different combinations of first gas flows and vaporized down settings, and this is how we then determine performance. We compared the weight loss from this one to the weight gain of that one, of course making a correction for the previously measured effect of CO2 via its effect on water generation. And here's the result. Over a range of 0.2 to 7 liters per minute, performance ranged from 100% to 93%. So very, very effective system in and by itself. So where does this discussion come into play? Well, it has to do with the definition of performance. So here are other studies. The company itself reports how effective the device is if you directly administer the desflurane into the charcoal, but we don't have these data, but they're on file. Then we have our study here, 93 to 100% efficiency of performance. And then we have clinical studies. I mean, one that was done by the Melier family with sevoflurane and have toric control low flow. And they found that 45% of all the vaporized desflurane could be captured by the charcoal. And then we have the Hendrickx study, and they actually looked at also clinical study in patients, and they looked at, well, let's have a look at how much desflurane disappears from the vaporizer, and then after the canisters are full, let's send them to the lab and extract all the desflurane possible. And then I found that they could only recover 25%. So big difference between here, I mean, this combination is very effective, and the clinical studies. Now both studies here, these clinical studies, so how do we explain this difference? I mean, both these clinical studies consider the amount left in the patient after emergence as a failure on behalf of the charcoal to, now I don't think that is a correct way of assessing the efficiency of the charcoal workstation combination. But still, there is a large difference between what's found clinically here and here, and why that is, we don't know. There must be other factors except the amount left in the patient that must happen somehow. Maybe endotracheal leaks, maybe CO2 pneumoperiodial losses, maybe the desorption process is not complete. So that's my conclusion. Good in vitro performance, but we still need to do the total life cycle analysis, like the transport of the canisters, the efficiency of desorption, etc. And if you assess these clinical studies, be careful with the interpretation of the word performance. Thank you.